Welcome back. In this video, we're taking a look at a couple of examples to help you get an intuition on analyzing the big O of different code pieces. And we'll start with a comparison between these two codes. Now, these two examples do the exact same thing. They both find the sum of elements in this sorted array nums. But which one is better? If they're both doing the same thing, which one should you go with? Well, for us to answer that, we'll first need to appropriately define better. What is actually better? What makes an algorithm better than the other? Well, in case of algorithms, we really only care about two things: time and memory. So, if an algorithm takes less time to execute than the other one, or if it takes less space or both, then we can safely say that this algorithm is superior. So let's first talk about time. How can we determine if an algorithm is faster than the other? Well, you might be thinking timers. Just start a timer at the beginning of our code, close it at the end, and we would be good to go. We got our time, right? Yeah, that's not a good idea. You see, timers cannot be a reliable way to measure a code's speed, since a code piece can run faster depending on the machine. If you got a supercomputer at your house, you're probably going to finish executing the code before someone with a regular PC. So, machine specs matter in terms of seconds needed to run some code. So we need to find a way to measure the speed of an algorithm or the efficiency of an algorithm without taking into account which hardware it's run on. Something that depends on the code itself, not the processor on your machine. So instead of timers, why not just count the number of operations of the algorithm? Just bear with me. Consider this example that we saw earlier. How many operations do we have here? Well, we got a multiplication right here, we got an addition, we got a division, and we got a couple of assignments right here. One for assigning an array to the variable nums, and one for assigning the length of the array to the variable n. Now, there is a key observation here, and that is that the number of operations don't really depend on the length of the array. So say our array was of size 1 million. We would still have the same number of operations. We would find the length of the array, that's one operation, then we would find the result of multiplying n by n plus 1 over 2, that's 3 operations, and like we see in the picture, the number of operations in this example aren't really affected by the length of the array that we are trying to find the sum of its elements. This is key. Now, we can basically say that the number of operations we have to do in this algorithm is constant. We just need to find the length of our array, do a formula, and boom, we have our answer. Doesn't matter if our array has a size of 10, 100, and million. The number of operations needed doesn't depend on n, doesn't depend on the size of the array. In that case, we can say that the time complexity of this algorithm is big O of 1. This is how we would represent algorithms with a constant number of operations, ones that don't really care about the size of the input. They would always have the same number of operations no matter what. Of course, we're going to talk more about this in later videos, but for now, I just wanted to give you a general understanding. But now that we're done with the first code piece, let's see the other one. So here we want to do the same thing. We want to find the sum of the elements in our array. But you see, things are quite different here. In this code, the way that we find the sum of elements in the array is that we loop over our array, and in each iteration add the current element that we're on to our answer. Let's start with counting the number of operations. Here we have n additions. Now why is that? Well, we would do an addition at each iteration in the loop. And since we're going to do n iterations, that means that we would have n additions. Similarly, here we have n assignments for the same reason, an assignment for each iteration. We got n iterations, so we have n assignments. Again, here we got 3n assignments, although this one might not be so visible. But under the hood of the loop, we do an assignment for the new value of I, because remember, at each iteration, the loop increment its counter I. So at each iteration, we assign I to its new incremented value. Similarly, we do n additions, because we do an addition to the previous I value at each new iteration to find the new value. We also do n comparisons, because each time we increment I, we want to make sure that it's smaller than n, because this loop only goes on from 0 till n. Once I reaches n, the loop should break. So the loop will do a comparison each time it increments I to verify that it's smaller than n. Also, here we got these three assignments before our loop: the nums array, n to the length of the array, and sum initially at 0. So basically, here we got 5n plus 3 operations. So the complexity increases as n increase. If we have an array that have a million items, our operations count would be 5 multiplied by a million plus 3. So as you might have guessed, the algorithm that doesn't depend on the size of the array is clearly the smartest way to go. Of course, we're going to talk more about this in formal terms, but for now, I just wanted to give you a quick overview and intuition of Big O. Now, let's start to formalize this a bit.